Alrighty then, let's go ahead and get started. Today we're going to be going over systems of equations solving by inspection. What does that mean? That means we are going to graph and look for where these two graphs intersect. So you'll notice that we have this beautiful background paper of graph, which will help us a lot. I recommend that you do this kind of a lesson on graph paper because we're going to be graphing and we have to graph accurately. Before we could kind of just go with, like, I kind of know what's going on. So for an example, if I saw y is equal to 2x minus 4, before I could just say we start at negative 4 on the y-axis. And then for the 2, I would say that we go up to and then to the right 1. And we'd be good. But when it comes to solving systems of equations, we're actually looking for where two lines intersect. And if we do that with just kind of a hand-wavy attitude, we're going to get a very inaccurate number for our solution. So it's really important for us to be a bit more precise than normal now. Do you have a question, sir? Nope, no question? Okay. Sorry, you guys are like really tiny on my screen and my glasses are broken, so it's hard to see you. The joys of teaching from home. So we're going to start off by looking at an equation or a system of equations, which is two or more related equations. So maybe we should start off with a definition.
No, like stumps and logs.
A system, Muriel? Thank you. A system of equations is a set of two or more related equations. A solution is a set of variables that make all of the equations true at the same time. So we're looking for a solution to a system of equations. Meaning we're looking for the values that we can plug into our variables that make all of the equations true at the same time. The easiest way to do that is by using something called the Mark I eyeball. In other words, you'll look at them and you see it. To do that, though, we need to be able to be really, really, really good at graphing. So, do you guys have this stuff down? Can I move down? Okay. All right, let's go ahead and move down. And let's start with our first two graphs. So here we go. First, a vertical axis that is poorly drawn. And then a horizontal axis that is not quite as badly drawn. Let's see if I can redo that vertical one. Make it a little bit neater. Just a little bit neater. Okay, so here are my axes. I try to follow the grid as best I can, but it is what it is. And then from here we're going to have two lines. One of them is going to be the line y is equal to x plus 4. So I start at 4, 1, 2, 3, 4, and make a dot. My slope is 1, so I go up and to the right and down to the left, one space each. And that creates our slope. So here's our first line. The second line that we're going to be looking at is y is equal to negative x plus 6. So if we're graphing that one, we'd start at 6. So we started at 1, 2, 3, 4, 5, 6, so we're starting here. Now since the slope is negative, that means I'm going to be going down 1 and then to the right 1. Right? Negative slope goes down, positive slope goes up. So from here, I would start at 6, and my slope is negative 1, so I go down 1 to the right 1, make a dot. Down 1 to the right 1, make a dot. Down 1 to the right 1, make a dot. And so forth. And that creates this line. And then we ask one of the most smart aleck students in the classroom, where's the solution? It's kind of like that question, you know, find x, right? And they just point to x and say found it. Right? We're kind of doing the same thing. We're asking, where's the solution? Why are they both true at the same time? Here it is. Hey, we found it! But then we're asked, what are the x and y values associated with that solution? Well, for the x value, just go over one space, so x would be 1. And then for the y, we count how far up we go. 1, 2, 3, 4, 5. So it'd be 5. Now, does that make both of those equations true at the same time? Well, let's find out. We'll find out by plugging it in, right? So I'm going to take the solution and see if it works for the blue equation. The blue equation was y is equal to x plus 4. So if y is 5 and x is 1, does this make a true statement? Is 5 equal to 1 plus 4? Yeah, so hey, we're good to go. Congratulations, we got one right. Yay! So checks for blue. What about for red? Well, y is equal to negative x plus 6 for the equation. So we go y, which is 5, equal to negative x plus 6. So is 5 equal to negative 1 plus 6? In other words, a 6 minus 1, 5. The answer is yes, it is. So is it true for both equations at the same time? Which tells me that 1 comma 5 is the solution to our problem. Pretty easy? Yeah, I think so too. Just looking at it, it seems like all we have to do is graph on good graph paper and find out where the two things intersect, and we're good. All right, so let's go into another example. One that might be a little different. So I'm going to go ahead and come down here. And again, I'm going to attempt to draw a straight line. So we know what happens when Mr. O'Neill draws a straight line. If Mr. O'Neill ever drew a straight line, the world would instantly end. Which means, ladies and gentlemen, we're perfectly safe. Because I can't draw a straight line to save my life. Now, on this one, we're given two new equations. And our two new equations are, for the first one, y is equal to x plus 3. And for the second one, we'll have y is equal to x plus 1. Thank you. I'll take all the blessings I can get. So for y is equal to x plus 1, we start off at 1. And we have a slope of 1. So up 1 over 1, up 1 over 1. Down 1, retreat 1, down 1, retreat 1. And here's our beautiful line. It's very royal because it's purple. And this next one is how I'm feeling right now. Just a little green. We start off at 3 because it's x plus 3, so there's our starting point. Our slope is the same, it's still 1. So I go up 1 over 1, up 1 over 1. And then I ask myself, all right, here's my second line. There's my first line. And when are these lines ever going to intersect? Never, right? By definition of parallel lines, they don't intersect. These are parallel lines. So if they never intersect, what can we say is the solution? Okay, I think I heard it, but please yell at me. All right, let me rephrase that. Yell at me with the answer.
No solution.
There you go. So since they never intersect, there's not going to be a solution. So this is no solution. So does every problem have a solution? No. Sometimes there's just no solution to the problem. That's just something that people have to learn. Oh, by the way, what do you think would happen if they ended up being the same line? Like if I had y is equal to x plus 1 and then I chose to graph y is equal to x plus 1 again. What's going to happen there? They become the same line, right? And if they're the same line, how many solutions do you have? You'd have infinite solutions. Okay, so no solution is if they're parallel. Infinite solutions is if they're the same line. Let's move on. All right, let's take a look at oof. Let's say that I have y is equal to x plus 1. And I'm also given the equation y is equal to 2x plus 2. First question, is this going to have a solution? Yes. How do I know that? Yeah, the slopes are not the same. If the slopes are different, oh wow, that's a horrible circle, Mr. Ring. I'll try it again. If the slopes are the same or are different, then you're going to have a solution. If the slopes are the same, then there will be either no solution or infinite solutions. So since I have a slope of 1 and a slope of 2, these are two different types of slope, that means we are going to have a solution. So if it has a solution, what should we probably do?
With a problem.
That's what we've been doing since the moment we looked at it. So we know there's a solution. What should we probably do? Well, my little one in the room said find it, and my little one is correct. When you have a problem, you should probably find the solution. And then you should implement the solution. For an example, I'm coughing a lot. That's a problem. A solution. Use Halls to make it so that I don't cough as much.
Take cough medicine.
Exactly. That's precisely what I did. So let's go ahead and graph this guy. So we got our vertical line. We got our horizontal line. And let's see what we've got going. We should probably color code these guys. So I'm going to make this first one pink. And I'm going to make the second one, what, blue?
Green.
Green?
Yeah.
Okay, so the second one will make green. Alright, so for 2x plus 2, I start off at 2. 1, 2, make it up. And my slope is 2, so I rise 2, run 1. Rise 2, run 1. I can also drop 2, retreat 1. Drop 2, retreat 1. That creates this beautiful line. Oh, that was awful. Let's try it again, Mr. Neal. Here we go. Now we go for the other color, the manly pink. We start off at 1. And our slope is 1. So we go up 1 over 1. Up 1 over 1. Up 1 over 1. We also go down 1, retreat 1. Down 1, retreat 1. Now I have a second line. And I think we already see where these two lines are going to intersect, don't we? I notice that both lines intersect right there. So that is at the coordinate point of -1, because I went to the left 1. And then on the y-axis, I didn't go up or down, so that would be 0. So the solution the solution to this system of equations would be at -1, 0. Alright, so for this solution, we'd start off at 4. Make a dot. And since the slope is 3, I'd go up 3 to the right 1. And then it kind of goes off scale that way, so down 3 to the left 1. We get a pretty steep line here, so we have to be a bit careful with it. For the other one, we start off at 7. And then we go down 3, and then to the right 1. And I think we see a bit of a problem here, don't we? There we go. We have a little bit of a problem here, don't we? Where's the solution? Where's the solution? Is that an easy point to figure out? Is that like at 1/2 comma, what is that? 1, 2, 3, 4, 5.5?
Yeah.
Or is it at 2/3, 5 2/3? Or is it at 1/3, 5 1/3? Could it be at any of those 3 spots?
Yeah.
Yeah. So, unfortunately for us, this is a great case of what happens when things don't work out nicely on a graph. This is the major flaw when trying to solve a system of equations by graphing. You can do everything right, you can know there's a solution, you can get kind of close to the solution, but do you know for sure what it is? The answer is no. No, we don't know what it is, not unless we work really hard at figuring it out. Alright, let's do another one. Hopefully this next one will be nicer to us. Okay, this one's not nicer to us, but we're going to go over it anyway. Let's say for a moment that we're given a system of equations of, let's see, that's 6x plus 2y is equal to 12. And then on the next line, we're going to have 12x plus 4y is equal to 24. How do we go about solving this one? Can we graph these? Do you guys remember how to graph in standard form? Okay. We can solve this one. This one's actually going to be super easy to solve once we get it down. And actually we can graph it. Even though the numbers seem to be really large, they're actually not that bad. So what we do is we use something that I like to call the Nixon method. Because if you if you knew your history, Nixon was a president of the United States who was caught in a cheating scandal for his election. And that scandal was called Watergate. And with the Watergate scandal, he tried to cover up what he had done wrong. So what we're going to do is we're going to cover up one of our variables on each one of these and use the remaining amount to figure out where we're supposed to go. So I'd start by covering up the 6x. When I cover up the 6x, what am I left with? I'm left with 2y is equal to 12. So if I know that 2y is equal to 12, then what must y be equal to? Six. Thank you. Glad we've got some participation going. Yeah, we divide both sides by 2. 12 divided by 2 is 6. So I start off at 6 on the y-axis. So I'm going to start off right there. Now, to solve for the rest of it, for the other part, I would cover up the y, and I'd be looking at my x. What do we have here? 6x is equal to 12. So I'd write down 6x is equal to 12, which means that x must be equal to 12 divided by 6, which is 2. So I go to 2 on the x-axis. Now that I have my 2 points, I can graph them. So there's my first line. Now for the second line, I do the same thing. I cover up the y, and what am I left with? 12x equals 24. So if 12x is equal to 24, divide both sides by 12, x happens to be 2. Okay. Huh. I would say that something fishy is going on here, but I won't be baited into making that pun. Thank you, thank you.
Sorry, I didn't catch that. What was it?
Then we cover up the x. What are we left with?
4y.
Equals 24. So I would say 4y equals 24. Then we divide both sides by 4, we get y equals 6. Okay, well, let's graph y equals 6. Uh-oh. Alright, well, just like the fish, we're going to have to finish this one off. Because I think that these two lines get along swimmingly. Because they're the same line. If I could draw, which I can't. Which is sad. There. So if they're the same line, what's the solution? Infinite solutions. This problem has an infinite number of solutions. Alright, so what are we supposed to take away from this? One, you need to get good at graphing. right? If you notice, every single one of these required a graph, but that's normal for when you're solving a system of equation by inspection, is you're going to have to graph everything. Second thing, if their slopes are different, are they going to intersect?
Yeah.
Which means you're guaranteed one solution. If they have the same slope, are they guaranteed to intersect? No, so you might have either no solution or infinite solutions. Either way, you're going to have to be able to graph these things. Sometimes they'll work out nicely. Sometimes they won't. But you still need to be able to graph all of them accurately. Alright, with that done, time for everybody's favorite. I know this is a word that I love to see.
I used to love to see this word.
So this one's just going to be really easy, 5-1. And oddly enough, we're going to do every other problem with a prime example being the odds. I know you guys saw that line of thought coming. Because I'm obviously hooked on puns from all the fishy things that have been going on. So unless you want me to continue with all these wonderful puns, which tend to smell bad after a while, and you don't want me to fillet you with more, I'd recommend pulling out your books, going to section 5-1, and start working on all the odds.